Okay, in this example, we want to go through an analysis of regression. Let's go ahead and take a look at an example problem. We have the relationship that we'll be investigating based on profitability and growth. So here's the problem. The following table, which is on the next slide, shows the mean annual percentage return on capital, which is profitability, and the mean annual percentage sales of growth for 8 aerospace and defense companies. Compute the correlations between the attributes and develop a regression equation for profitability based on growth. Can we conclude that the slope of the regression line is negative? Here is the data that we'll be investigating. We have the 8 different companies, the profitability and growth. So let's go ahead and take a look at that starting file. Okay, here is the starting file. We first want to compute the correlation between profitability and growth. And of course, we could do that with a formula of correlation. Let's go ahead and do that. The correlation between the two would be CORREL. Array 1 doesn't really matter. Let's put the correlation of profitability, comma, growth. And the correlation is, in fact, negative in value. But we later have to determine if this is statistically okay to say that this is a negative value, because it could be statistically equal to 0, or statistically equal to actually something positive. So let's go ahead and investigate this problem a little further. One of the first things we'll have to do is identify if profitability is an X value or the Y value. Now in our problem, we have stated here, develop a regression equation for profitability. So we know that that attribute is going to be our Y, our dependent attribute, and therefore growth will be our X. So if you want to provide some format over there, go ahead. And now we're in a position where we can go ahead and perhaps graph this just to visually see what's going on with our data. Let's go to Insert, Scatter, first Scatter, and right click, select Data. And what I'd like to do is just see the relationship for myself. So we can give this a name. Let's call it profitability versus growth. Our X values are going to be growth. Our Y values are going to be based on profitability. And let's hit OK. Let's hit OK again, and let's go ahead and provide a layout just so we can document the two. This Y is profitability, so let's just reference the cell there. Let's reference the X-axis cell to growth. And what I tend to do, I think this is a wasted space, so I'm going to change where the legend is, and I'm going to put it underneath. So I think that's a better utilization of space myself. If we were to plot a regression line through this data, we could simply do that by a right-click, add trend line, and it's already set by default on linear. We could display the equation on the chart and display the R-squared value on the chart. We could even make the line a little bit thicker to 3 so we clearly see the linear relationship. We have the equation in this box, if you will, and normally I shade that in and provide an outline so it's very clear. So we'll notice actually that we get our slope and our intercept coefficients right from the add trend line. Okay, so this is definitely one way to do it. Actually, we see our R-squared value too. I just want to show you that R-squared is nothing more than taking the correlation coefficient and squaring it. So we get exactly the same value as this analysis. Of course, this is a dynamic way, and this is also dynamic based on the data that we've highlighted for this graph. Okay, we have another option, and the option that you'll want to do your analysis from, because it actually gives us more insight to the problem. So let's go ahead and go to Data Analysis and find the regression option. The regression option requires a value, a range of y, a range of x. Our y we've determined is profitability. Our x is growth. And we do have labels. Right now, I'm not going to worry about constant is 0 or confidence level. We'll get to that later in the videos. I do want to put the output range underneath of my report, let's say here, and I'm going to ignore everything else. Now, with any type of regression analysis, I just want to make one comment. We do have the underlying assumption that our data is quote-unquote normally distributed. So a lot of these options down here provide evidence if that assumption is good. We're going to assume that all of the information that we contain in these examples are in fact normal. Let's go ahead and hit OK and take a look at the results here. So we get the multiple r, we get the r squared. R squared is exactly the same as the value calculated up here and on the chart. We have the adjusted r squared, which is a topic for another day, standard error, something we're familiar with, and of course observation numbers, sample size. And then we have our Anova table. This is really the most important portion of the analysis. And what we want to do is first just review what regression means. So I want to document just the equation for now. So the equation, this linear relationship that we actually have developed is, I'm going to put a single quote so this doesn't think it's a formula, is equal to A plus M, or let's say B, doesn't really matter, A plus BX. And of course these letters are arbitrary. A, let's write it a different way. Intercept plus the coefficient or slope times our x. Okay. Well, let's break this on down further. We know the intercept. Let's just write that again. It's in the table above. The slope in the table above is actually referred to as a coefficient of growth multiplied by, multiplied by our x value, which our x value is going to come from growth. Okay, and it's given me a name error because it didn't recognize that single. I must have hit something else. Okay, so let me merge and center these. So these are all just different ways of representing this equation, and I'm just thinking about a good way to format this. So we have A plus BX, which is also equal to intercept plus slope times your x. In the table, we refer to this as a coefficient times our x value. Our x value is growth. And if we wanted to write this just one more way, let's just go ahead and plug in the coefficients. We have for the intercept above in the table right here, 17.9. I'll just leave it as one decimal. Plus the coefficient for growth, which is actually a negative 0.03 times our x value, which is growth. Okay, so that's really our equation. The equation for this, of course, is profitability. Okay, so profitability, in other words, equals the relationship 17.9 plus, and this is again a negative coefficient, so maybe to make this a little bit easier to see, we'll just put a minus sign. So 17.9 minus 0.03 times growth. That's the relationship we defined. So now we actually have to determine whether we can statistically use this equation the way it's presented. And the way that we do that is we're going to have multiple hypothesis statements. So we're going to have an H0 and an H1 for the intercept. Let's go ahead and format that so I can reuse this code or the cells I'm developing here. We're going to have another hypothesis statement for the growth, and that's all we have. We have the intercept and growth. So those are the only two factors that we need to explore, and our H0 is that we're testing, does the intercept equal 0? And I'm just going to go ahead and give us some more room in this spreadsheet with the merge across, just so the text doesn't overflow. The alternative for the intercept is that intercept does not equal 0. So statistically, it's something other than 0. For the growth, it's the same thing. Does the growth coefficient equal 0? Or does the growth coefficient does not equal 0? So this is what we need to determine in our investigation here, and that's exactly what this table up here does. Okay, one of the other things I should mention, most of what I've been talking about comes from this table. Let's go ahead and discuss what this actually means too, because it's not to be ignored, but actually you can tell the results from this table if you investigate this table. So what this is actually saying, it's an Anova analysis, and it's telling us that at least one factor is significant. Okay, so if we were to write that hypothesis out, let's just do it. Let's see if it'll allow me to copy this. I'm going to paste this here and say Anova. And the hypothesis of the Anova test, which is right here, is that, I'll just write it this way, all coefficients and intercept is equal to 0. Now, of course, what the alternative is, all coefficients and the intercept is not equal to 0. Okay, so what this is telling us is, do we have a situation where at least one factor is significant? And since we have multiple factors here, I don't like to write the alternative this way. At least one coefficient or intercept is not 0. That's really what we're dealing with. So the F test is, or the F stat is 0.02. The F critical, which is documented significance F, is 0.8. So we have an F stat that is less than F critical. So we can claim out of this analysis that yes, we do in fact have something that is statistically significant. It doesn't tell us what. It doesn't tell us if it's a coefficient or the intercept at this point, but this test does conclude that at least one is significant. And that's the same thing as saying at least one coefficient or intercept is not 0. The only way you can be significant is if you're not 0. So at least one coefficient or the intercept is not 0. That's what our conclusion is. And maybe what I'll do is I'll just put conclusion. And we are concluding this. At least one is. Or maybe I'll just put an arrow and an X to demonstrate that there. Okay, so our conclusion is, for the first one, is that it's at least one is not. What about the intercept? Now we're figuring out which particular one is significant. Okay, so that's the intercept. Let's take a look at it. The p-value in this analysis is 0. So the p-value being 0 would suggest that the intercept is something other than 0. Well, let's take a look at why I even looked at the p-value first. You'll notice that I actually had the test statistic, but the report did not give me any information as far as what the critical t was. So I have to make inference about this intercept based on the p-value. And let's go ahead and I'll show a couple decimal places there. So what we're actually seeing is the p-value is very small. A very small p-value means your test statistic is way far away out on a tail. If you're way far away on a tail, you're going to reject the null and accept the alternative. So we are here. Sorry, we are here. We're accepting the alternative. Okay, so we have that conclusion. I want to tell you another way to analyze this if you ever get confused about the p-value. We have these lower and upper 95s. And what this is really referring to, if we were to draw this, we have a coefficient here of 17. Okay, I'm going to put my analysis on the side after I bring up my paint. And I want to demonstrate what we actually have here. We have a situation where this is going to be the x-axis, and I'll actually just use a line for this so it's not as sloppy. So we have our x-axis. Our coefficient is 17. So let's just say it's here. It's 17. Well, why is this 17? Well, it's because this is based on the center point of the upper and lower values. The upper 95 value is 27. The lower 95 is 7.9, which means this is normally distributed, so it looks something like this, where the mean is centered at 17 and the 95% confidence interval, if you will, looks like this, where here are the tails, and we're going to put 2.5 alpha here. I'll just say alpha, well, better go ahead and put 2.5 alpha here. This is 2.5%, and this is 2.5%. So it's telling us the width. We can be 95% sure that the true value of this intercept belongs to a range of 7.9 and 27. For our equation, we pick the center of that. Okay, so what we have here is if we were to extend this line over, I'm just going to put maybe in a color green that 0 lies here. So we have 0, we have 7, 17, 27, all in ascending order. So what we're saying is between these 95% confidence intervals, 0 does not belong to this range. Okay, if you can say that, then statistically we can say that this intercept is something other than 0. So therefore it is significant. Okay, so the other way to look at that is maybe you don't want to evaluate the p. Maybe you go straight to the 95. And the quick and easy way of analyzing whether the intercept is significant or not is just to look at the upper 95. It doesn't have a sign change, in other words. You go from positive lower bound to a positive upper. 0 is not in that range. So if 0 is not in that range, we have to conclude that it's significant. And it's significant because it's something other than 0. What about growth? Well, growth, first of all, has a very high value of p, which means we're very close to the median, the middle of this normal distribution. Well, that would mean that we would be in the do not reject region. So we can conclude that the growth coefficient at this point is in fact 0. Now let's look at the alternative ways of investigating this. The lower 95 was a negative 0.05. We cross 0 and enter the upper 95 value, which is 0.5. So 0 is within this range. So if this is in fact including 0, then we say it must be equal statistically to 0. So to answer the question above, develop the regression equation for profitability based on growth. We've done that. Can we conclude that the slope of the regression line is negative? The slope of the regression line for this single variate regression analysis is the coefficient of growth. The coefficient for growth is 0. So yes, we can conclude it is. So in other words, the growth is not explaining the profitability that our company is seeing.